Okay, let's start. So here we are, lecture 3 in economic engineering, and what I want to do is continue the discussion we've had on Newton's laws of motion and how they apply to economics. Now, we are devoting 2 lectures to this, and there's and maybe more, but there's a very good reason, because this is really the heart of what economic engineering is. And this is also, every time you look at somebody else who has a different approach to do this, again, Koen came today, he found another guy, it's very interesting what he's doing. What's the difference? Well, the difference is always, it seems to be the same, is that the way we use Newton's law, and they either don't or use it in a different way. I don't think that anybody uses it in a different way, they just don't.
Well, they some used it
in a different way?
Yeah. Say that price is a force.
Price is a force, but what is momentum then? They won't say anything about it. And Newton's law associates momentum to the force. So there's one thing saying a price is a force, but then not saying what momentum is, then you're not using Newton's law, then you just have the old primitive idea or pre-Newtonian idea of a force, right? So before Newton, people knew about a force, and it was something that would bring equilibrium, and if they didn't balance, then it would knock things out of equilibrium. But what they didn't know, that if the forces didn't balance, then how the body or the mass would change its equilibrium in a quantitative way. This is what we now call dynamics. So Newton's contribution is precisely that. He looks at all the forces, you add them up. If you have a net force, then okay, how does this affect the position? And his answer is proportional to the acceleration, right? The change in velocity. Okay, so if you see approaches where a lot of approaches, they will take, okay, price is like a force because if the price is high, people want to buy it, so there's a lot of force, et cetera, et cetera. This is not quite right, as we will see and as we've already argued. But even if it were right, then what is, if price is the force, what's the time integral of this price then, which has to correspond to momentum, and there's no answer. So then you're really not applying Newton's law, you're just doing more statics and not worrying about the dynamics, how things are changing. Now I switched presentation software to do this beamer, which I should have done a long time ago. But now what I'm able to do is make these fancy pictures. So here's our tetrahedron of state. And I just made this a little bit transparent. I was thinking of making some dynamic effects, but they just distract. So if we go back to the tetrahedron of states that we've introduced in our introductory lectures, what we're talking about is just these 2 bonds here, this one and this one. Okay, so Newton's law gives us a very small thing, and in fact it's symmetrical with the stuff that is really easy, how you add up a flow to get your stock and how a stock relates to your wants or your forces. So you could just finish this lecture by saying, well, it's kind of all the same, so there you are. Huh? If you look at it this way, there's something totally trivial about Newton's laws. And yet, it takes forever to understand this stuff and get it right, you know? And Newton's contribution to science should really not be underestimated. Before Newton, there was, of course, this notion of force, which is a situation that Koen also describes. You have now in economics, there's the force of the man, then there's this. But there were different types of forces for different applications. So famously, they had terrestrial mechanics, how things move on Earth. That was cannonballs, because they were quite interested in shooting each other. And then they had terrestrial mechanics, that was the movement of the planets, that they were interested in because they wanted to navigate, and at night they got to look at where these stars were. So they usually would navigate to some other place where they could shoot off a cannon then and blah, 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 blah. But they would switch around. One they call ballistics, and the other one they call celestial mechanics and the works of God, and they were not united in any way, and they were separate fields of study, and they were really very important and long-time fields of study, and Newton united those. He says they're all the same. He famously quipped that the moon is falling, and he proved that. So in one fell swoop, the guy puts everything together and he quantifies it so you can say everything that's happening time with either your cannonball or with your planet. Now a similar situation exists I think in economics, and this is what we're going to try to leverage here. So in economics, there's all these notion of forces. There's the force of demand, there's the force of this, and usually these things are called wants. So why are things moving? Why do you have equilibrium? Because I want this and you want it also, and we somehow balance this out to make it fair. Then there is a notion of price. And these wants of ours, they endow things with a price. So why are cars expensive? Well, because people want them. Why is gold expensive? Why people want them. Why are diamonds expensive? Well, people want them. You know, why is water so cheap? Well, people want them, but there's a lot of people who want to get rid of it, you know, because they got too much, you know, and as it results, the way it falls out the equilibrium, the price becomes really low. All right? So you'll see that in economics in general, this equilibrium and the dynamics of the prices works in the same way. The wants, they kind of add up and balance with other wants, and if you have a net want, this is going to move the price. Okay? So this is what this thing says. So the price movement is something that was a concept that was around by Adam Smith. It was formulated, and it's a famous concept out of an invisible hand. So Adam Smith, and most of you learned this thing about the invisible hand, that everybody's self-interest moves the market somewhere. It's an invisible hand that's pushing and pulling. Now, what are pushes and pulls? Well, think about it. That's got to be a force. In fact, the mechanics of pushing and pulling was exactly what was underlying the idea of the scientific idea of a force. You start with an intuitive notion of a push and pull, and then Newton quantifies it by using defining what he means by it through a force, okay, and how it changes momentum. So, in some way, this lecture could be called, if I wanted to be funny, is like making the invisible hand visible, or visualizing the invisible hand. Right? So we take this invisible hand that's somehow mysterious, that's moving those markets to equilibrium, and we're trying to get to the essence of that by comparing it to how in mechanics of force moves everything to equilibrium. But what our results are a little bit more than just this equilibrium, which is what economists are quite happy about to go. It's also that we immediately, thanks to Newton, know how fast it will go to equilibrium. So we will know the dynamics. With this dynamics, we can build systems. LTI system, this system, that systems, and we can start doing real control, because what is control? That's influencing the way things move to equilibrium, and at the same time possibly influencing the equilibrium state where you get to, right? So your controllers will try to go to the equilibrium state, and you make some PID controller, you're sure you have enough I action, so you get there, and then you have enough D action and proportional action, so you can control the transient, how you get to the equilibrium state. But for that, you will need a model. So this idea is Adam Smith. Now, there's another idea that, and this is Newton here, who comes up with how the invisible hand relates then to this momentum. So we can match up Newton here with Adam Smith, at least in some spiritual way. All right, so Adam Smith never went so far as to say something like this. Now, how a mass relates the price and the quantity demanded, or how demand relates the price with the quantity demanded, was done by Marshall. And this is called the law of demand. It really isn't a law. It's more well, maybe it is a law. It's always difficult to say what is a principle, what is a law, what is a, you know, now. Huh? So we'll leave it at a law. This corresponds to probably Descartes and Huygens'. But in mechanics, it's not called a law, it's just called the definition of momentum, because we consider there are other ways to define momentum. So there are things that don't have a mass, for instance, like light, that do have momentum. And Newton's law will still be valid, but this definition of momentum will not be valid. All right? Now, mechanical engineering is rare, so rare that it just never occurs, I think. Maybe in this department there are some guys looking at light. There's a whole section. But otherwise, we always think we look at massive bodies, and that's what we'll mostly do in this course as well. So this is what I want to do in these 2 lectures today, is to scope this out and make this all specific. So Newton famously quipped that he was standing on the shoulders of giants, and he was talking, I think, predominantly about Galileo, and well, his name will come up in these lectures as well. And the way I like to see our efforts today is that we'll be also standing on the shoulder of one giant, namely Newton. Our idea is just to steal his ideas and apply them to economics, okay? So we're not going to worry ourselves too much about whether this is true or not true, you know, and we're just going to say, okay, we'll take this superstructure and we're going to try to apply it as well as can, and then let's look at the consequences, okay? That's our goal here. So we're real engineers, and we're not going to worry about the philosophy of it all. And there's a motivation for it, and maybe it bears repeating. This was done before, and this was done by Maxwell, who saw that electrodynamics was also parallel to mechanics. He just figured out that a voltage was the same, you could view it as a force, and momentum as magnetic flux linkage, and all these things. And he sorted it out, and with that came an ability to model electrical systems just as if they were mechanical systems using these same laws, basically, okay? So we're in this tradition to try to do that. Now, if you're a physicist or maybe a philosopher of science, you would wonder at this and say, well, isn't it beautiful that nature has this one way of ordering things and yaga daga daga. I don't want to take that approach, okay? I want to see this in a different way, like an engineer, is maybe spend a little bit of time wondering why it is that we humans tend to model things always in the same way. So apparently we think of nature in this way, quite intuitively, and it is very hard to formalize, but once we've done it, it's kind of clear. So we approach everything from this mechanical way, and I believe it is because that's how we were, evolved, you know, to throw spears and rocks and run around, and so we have a very good intuition for how the mechanical world around us goes, and maybe that's also the reason why mechanics is kind of the mother of all the sciences, and then all the other ones just are analogous to it, and so is economics then. Now what I will find kind of interesting of this effort is that when it's done, we'll look at concepts like momentum and energy that will correspond to a price, or energy will be surplus or some kind of income. And for me, but the thing that's kind of surprising is that, you know, concepts like momentum are always a little bit fuzzy. And what's the difference between momentum and energy? You always get a bit confused. But you never get confused between price and income, you know? Somehow that's really clear. I think because if it weren't clear, you wouldn't be around here. You'll just be, sitting on a bench without any money, of course. But so there's a sort of cross-fertilization where you deepen your understanding of mechanics with this kind of economic engineering. So let's just quickly recap what we did last week. This was Descartes stuff, the definition of momentum, P is m times v. And it corresponds with what's called a demand schedule. A schedule is a thing where they write it down like in a table. This is more like a demand line that I drew, or curve. And here I just plopped this one out of Wikipedia. So here's your typical one. This is a demand line. This is a supply line. And here's what they show is a shift in this demand line. So they imagine that something happens in the economics, this whole thing shifts over. You see they're curved. You see that they don't put any units here. There's no real point of zero. They could have drawn this axis over there. There's a couple of interesting things. Now, in order to get that in this shape, what we need to do is, instead of two graphs, we got to get only one graph, right? There's no, you see, remember how Descartes had an absolute value sign here? So nobody knew what to do with the negative velocities. They just kind of plotted it like this. And then Huygens came and fixed this problem. And Huygens' fix we somehow have to figure out. So that instead of two lines, a different one for demand and supply, we just have this one line covering both. And this is important because economists often think of either I'm a consumer, so I'm demanding, or I'm a producer, I'm producing. All right, I'm offering on the marketplace, okay? But if you spend some time on the stock exchange, what I did, you'll see that that just doesn't really correspond to reality. A trader, he first buys, puts it in inventory, and then tries to sell, whether you're a currency trader or maybe a car dealer. You first buy the cars, put them on your lot, and then you sell them, and then you buy again, and then you sell. Or you may restock them, send them back to the factory. Okay, so there's no, you keep switching between demand and supply if you're a trader. So this kind of setup is not flexible for us, enough for us, all right? So fortunately, the Newtonian approach will force us to get this into one shape. Now the other thing that you can't have is that these things curve around. This thing has got to be a constant. Mass has always got to be a constant. Even in relativity, it's a constant. Now here, it's not. Here, there's a slope here. Here's this different slope. So the slope is the mass. It's the inverse of the mass in this case. No, the slope is the mass. Elasticity is the inverse. So we can't have this. So we'll have to explain why they see what they see here. All right? Or we'll have to explain that in our system we can deal with this in a different way. So we can hold on to the idea that the mass is constant and at the same time be able to explain why, if this economist is measuring this, he'll be seeing that. All right? And then finally, what are these shifts? Now you see this thing is always going through zero, because if you plop in zero here, it's there. You can't just add something here. It's not an affine transformation, it's linear, right? So what's up with these shifts? Where do they come from? So that's what we want to do. We want to carefully step through his laws, and if you follow them, you'll realize that you can systematically get rid of all this stuff, all right? And the other thing you'll realize is that not only determining where equilibrium is, you can start saying how fast you're moving along this to equilibrium, all right? And in fact, your notion of equilibrium is going to be a lot more broad than just the crossing of two lines. When you read economists, you have a strange feeling that when they want to talk about equilibrium, they always reduce it to two lines that cross, and then the point where they cross is equilibrium, right? Whether they're doing macro or micro or that's just their equilibrium. And it's a little bit strange because nowhere in engineering, when they teach you about equilibrium, do you see these kind of figures. I mean, it's always with a balance of forces, and you figure out when the forces add up to zero, and then pots, you're standing still, okay? And then you're at your equilibrium point. There's no more motion. So we also have to give up this holy grail of every equilibrium is just the crossing of two curves. Okay? But this is our starting point. So now to get rid of these two lines, and let me say this. How do they get this in one graph? So here's the problem. They always need price to be positive. They don't have the notion of a negative price. Just like Descartes, he couldn't understand there was a negative amount of momentum or quantity of motion, as he called it. So what they actually do is they call this the quantity demanded, and the quantity supplied actually runs the other way. They'll say it runs this way. That's all they'll say. They'll forget to put it on the picture. They also don't put any units on it and that kind of stuff. All right? Now, we don't want to do that. So what we want to do is have a notion of a positive direction for our quantities or our flows and a negative direction. All right? Now, a number that can be positive or negative in one dimension is a vector. It's just that a vector in one dimension, the direction is either a sign. So one of the big differences, I would say, of the engineering approach and economics is the use of vector analysis, all right? So that quantities don't always have to be number. It is not just a number. A number can come in many forms. It can be a scalar, it can be a vector, it can be a tensor, it could be all kinds of more complicated elements. Whereas an economist will just think of a number more like a, yeah, I don't know, like he's counting pizza boxes or something. Always a positive number, right? And really negative, and definitely not as a vector or a tensor or something like that, all right? But we need to. So what we did last lecture is to say, well, Newton's analysis takes place in space, and it's a normal three-dimensional space, 1, 2, 3 dimensions. And what corresponds to these dimensions then if we have economics? Now, the best way to look at that is that what corresponds are various commodities. So here we have two commodities. This one could be oil, and this could be pork bellies or something. Why do I say commodities? Commodities is just a name economists give to when you have a product or a good that you can't distinguish one from the other manifestation of it. So if you have oil, one barrel is the same as another. So antiques is not, houses probably also not, you know, unless you have these standard houses, you know. So that allows you just to plot them on a dimension and say, gosh, I have so much of it, and I have so much of this one. Right? Now, they will do this here. This is also out of Wikipedia. I plot these things out of Wikipedia, not because I think it's so great, but more to emphasize this is how generally people would think about it, right? If you can throw a bunch of people together, economists together, and make them build a web page on it, they'll draw something like this, right? That's why these things are here. And again, they don't like negative numbers, so they imagine two players, a party and a counterparty, and they have an endowment. So this is the total amount of the commodity. This is the total amount of the commodity Y. And then in this case, Abby has none, and Octavia has all, and then the other way around. And so they have two axes, and they can keep track with positive numbers what everybody's stock is of these two commodities. All right, and then they can trade, and then you know, you can buy some from Abby can buy some from Octavia, and they go like here, and this is called the contract curve. All right, so this is when they trade among each other. This will be the motion. Right. And here we are. I plotted this now just in a kind of frame where we would imagine Newtonian mechanics to take place. So I have the x dimension, the y dimension. This thing is in the plane. I got two commodities. I drew the economist axis here in, what is this? Yeah, sort of red and blue, cyan and magenta, I guess it is. And but then I say, well, that's not what we will do. We'll take some arbitrary points here. I took the center, but you don't have to. You can draw it anyway. Huh? And then I just have this as a sort of a reference frame. And then I can measure where any point is, like this point, by looking at how it is with respect to where it is with respect to this arbitrary point of zero that I just took. So this is a little bit what I would do when I describe a mechanical situation. I take space. Space itself doesn't have a natural zero, so I'll just take one, check, here it is, and I start measuring from there. So I'll just use some negative numbers to get this thing, positive numbers for that thing, etc. Then I can draw that same contract curve, but now I can already do a little bit better, you know, rather than just say, well, they're in equilibrium here or they're in equilibrium there. I can say, well, the motion will be along the contract curve, but because I have this nice coordinate system, I can say it's moving at a particular clip here. So here it's moving very slow, and here we're moving fast. And I can approximate that motion with a tangent vector. That's the original idea of a vector. Now you see mathematicians, they have a tendency not to view vectors that way, but to say, well, it's a column like this, or at least the mathematicians that do economics. But you see, this column is really not essential here. You could have chosen a totally different coordinate frame. And, you know, like this one. Huh? And then these numbers will be very different. This would be, I would have to put a prime here or something, because this is the prime frame, right? But it would still be the same vector, still be the same velocity. That won't change. So however I define this thing, it cannot depend on these numbers in any physical way. All right? So this vector is something physical. And in the same way, you have to see that this vector is something economical. It just says how, you know, at what rate Abby and Octavia are exchanging one good with another, you know, as it goes in time. All right? Now, what we chose as coordinate system is irrelevant. Whether we look at apples or oranges, you know, or two types of fruit salads containing half apples, you know, a little bit of oranges and lots of apples, and as opposed to lots of oranges and little apples, you know, so it will be a skewed coordinate system. So you don't have to take these pure things. You can do anything you like, any baskets, as long as you span the space. All right? So vector graphics vector analysis, what it does, it fixes this problem that you have to keep track of all these dimensions and how you chose a coordinate system and whose is what. You say, okay, I have a position. This is what the economists call an endowment, Q. At a certain point, you're at this position. This consists of all the different commodities you may have. And this is my trading efforts. And this is probably how I'm exchanging one commodity for the other. All right? How much I'm acquiring or disposing of. Okay? I don't know why I drew this vector now as it should have been a vector, right? This is just a point. This is a vector. If you give these two pieces of information and you do that for every possible point, then you have something that's called a state space. All right? So a state space, you can build it on these Edgewick boxes, but they're a little bit more. They will tell you for all possible points how you could be changing, so what contract curve could be. All right? And what we need to do with our dynamics is just to be sure that we have a set of differential equations or other type of different equations that will tell us if we're here, then what's the next step we're going to make. But not only just what are the allocations. This is wrong. This should be allocations. A position is called an allocation, and the total amount available is called the endowment. And I'm assuming the endowment here is infinite, okay? Infinite amount of oil available. This is, of course, not true. This is an error.
Also space is not.
Yeah. I mean, and maybe a wall here, right? Okay. So this little slide may feel like it's a lot ado about nothing, but nobody caught this error, so it can't be. So you just have to see this. So how do you get any economic situation into something that's worth doing Newtonian mechanics with? Well, you look at all the stuff that you model. I want to keep track of. I want to keep track of oil. I want to keep track of apples. I want to keep track of these grains of salt, and I want to, whatever you want to do. There's a whole bunch of stuff that you're not going to keep track of because there's infinite amount of other stuff. All right? Later on, we'll see that all the stuff you don't want to keep track of, we'll put that into a notion called entropy. All the stuff you do want to keep track of, you gotta, so those are the things that you can have I elements for, C element for, R elements for, transformers, all this stuff. So that's what it means keeping track of, okay? Those elements, you have to see how much where you are, your position or the allocation, and where you're going, okay, for the dynamics. All right, so far so good. We've just repeated what we've done, only in, I was going to say this. I did want to say something else. See, Newton worked only in a space of 3 dimensions, and he did all his work there. Then later people realized that that was limiting. So they switched, they extended it, they didn't switch, they extended it to something that would be called generalized coordinates. So they would have some mechanical system, now, that have way more than 3 dimensions. If you have like one mass, another mass, another mass, another mass, another mass, then you have at least 3, 4 distances you have to keep track of. And probably a 5th one, now, which is the distance to your inertial reference frame, all right? You could actually do it like this. So that's a 5-dimensional base space, and for each you have to have the velocity, so you're in a 10-dimensional space. That's way bigger than those 3 dimensions that Newton has, okay? So these are called generalized coordinates, and these could be anything at all, any amount of them, all right? We will just work in the plane like these Edgeworth box guys, but you have to keep in mind this thing just generalizes to very large systems, okay? Now, the simplest one is just a Cartesian thing, right? So it's like a Euclidean space, and you can think of that, the position also as a vector, although it really isn't. But you can have all other spaces. So, for instance, if you have this is a pendulum, nobody would take a point here and plot the x and y coordinate at another point. You will just think of this as one thing like they did here and just list the angle, right? And you say all the positions here are all the possible angles. Now these, after 2 pi, it's the same thing. So rather than a space that is a line that could be anything, it's a circle, all right? So this is kind of complicated. This is then a position. So there's a line in here as well. And there's another circle. And then there's this distance. So you see, they could be anything at all. They could also be angles. Now, if you go back to this Edgeworth box, you see that, of course, I can give these coordinates, but I could also say, well, somehow this is, and I think they try to do this, in total this amount, and this is my relative allocation, right? So if I have apples here and oranges there, and I'm trying to make a fruit salad, then I could say this is the total weight of my fruit salad, and this gives me how many apples I have per orange in that. The composition kind of gives me the composition. Huh? And this will be polar coordinates then for the same thing. All right? So This stuff is important in the banking application, for instance, where you look at credit and other things. We'll get to, I just wanted to mention it, that you can do this kind of thing. So don't get too stuck on the idea that this only works for simple commodities that they could have units of meters, meters of cloth, or kilograms of gold. But in general, I'll use this unit here. We could also do, I guess this would be better called a composition, huh? And then you also have these things like labor and capital. And like labor, you measure in man hours, okay, rather than in just man or something, or person hours, maybe you should say. One thing about it is if you have the labor is in man hours, so then what will be the velocity? What will be the quantity demanded? That will be in man hours per year or something. Right, but now I measure it per hour. And I can cancel this, and then the velocity would be in men, right? So you will see that you'll have a flow that is measured in men. If this is machine hours, or maybe you have a house and you rent it, you will have so many hours of use of an apartment or a hotel room, you know, it will be the same kind of problem, all right? So the flow then becomes something that doesn't look like a flow because the silly thing is canceling, all right? I wanted to mention that. When people model these things, it's just hard to imagine that somewhere in here this is canceling. So you get all confused. You think that labor force is men instead of man hours, and the flow is then men per hour or something, and you get all messed up, all right? So this is just a word of warning on how you choose these units, and also that it can be a little bit more complicated than this. For now, we'll just start with simple, we'll continue with these simple commodities. All right? But this is already interesting, right? This is a pretty complicated system, and you could see how this can already model something economic. All right, so this is some amount of some commodity, you can think of that. This you'll see as a composition of something. And now you have to kind of train yourself to think this way. All right, so now let's get serious. So this is, we laid the groundwork. We know now what space is, and we know now what the flows are. So we have ourselves set up to do Newton's laws the way Newton did it. Now, let me do the first law before the break, and then the second and the third law after the break. The first law is also known as the law of inertia, and I'd like to just call it the law of demand. All right? So how does this work? The first law is actually was Galileo who came up with this. He got it slightly wrong. So before Galileo, there was an idea that if you had an object, it would kind of create, and you left it alone, it would always kind of come to rest if it was going horizontally. So it had something in it that there was a tendency to move, but it always would just stop. And if you dropped it vertically, they had a different type of dynamics. There was this, that was Aristotle who formulated that, and the idea was that depending on whether it was fire or earth-like or fire-like or water-like, it had a tendency to take a velocity going down or up. So fire, it was believed, was some substance that would just always go up, all right? And water was a substance that would always go down, but not so fast as lead or earth or things like that, all right? And then the reason this came is if you took an object and you just dropped it, it would first accelerate. They wouldn't really notice that very well. And then they would notice that it came at some kind of cruising speed, right? So they would say, well, this is how we build our mechanics, right? So we have two different types of mechanics: when we're dropping down, when things are falling, and when things are moving sideways. Now, here you already see why Newton is considered a brilliant man. If you think about it, what did he say? He says, no, none of this is true. A body at rest goes at a constant speed, no matter what. Sideways, this way, that way, any dimension, all right? Then somebody puts up their hand and says, excuse me, Mr. Isaac, I just did the experiment, and I noticed that it's always false, right? There's not one experiment I can do to which your law is correct. So I cannot even, this is ridiculous, all right? So you got to appreciate the courage of this man to say, no, these are all exceptions. Your experiments are all wrong. You know, my law is still right. Although you can't verify the experiment, okay? We know he's right. We know it's all due to friction and various manifestations of friction, all right? But this is a big step, all right? And if you make these kind of steps, you're always ridiculed, you know, because it's obviously false, okay? And yet it's true. There's a joke that I'm just reminded of. There's a scientist, and his name is Murphy, and Scottish scientist. And he came up with this new law that says that if you take a slice of bread and you butter it, right, that you flip it, it will always fall down with the buttered slice down, right? So he shows up, and he says it's always true. So he shows up and with his law, he says, okay, here's the experimentalist, right? Let's test this. So this guy, he has his laboratory, he takes a slice of bread, and then he puts the butter on, and he flips it on the air, woo, bots. Buttered slice up, right? Mr. Murphy, your law is wrong, right? I just measured it. Well, Murphy says, no, obviously not. You buttered the wrong side, okay? The law is right. So this is what you got to see, all right? So this is what's going on here. The law is right, and you just buttered the wrong side, obviously, right? This is the position here. As soon as you notice that this law is not right, then you did something wrong with your experiment. If all your experiments show the wrong thing, then you all the time do something wrong with your experiment, okay? You have to imagine that it's not the case. All right? Now, what did Galileo get wrong? He kind of didn't see. He saw this. He famously threw these two things down the Tower of Pisa, and they came at the same time, and then everybody realized, well, you know, when they fall, they go at the same acceleration. He's right there. But he got it wrong with the planets, you know. He kind of thought the planets were in inertial motion, and that the circle was just another inertial motion. It's like a straight line, right? And it's not. There was gravity, and Newton, of course, sorted it out for him, all right? So we'll get to this. Well, no, this is, So this story is one. It's kind of complicated how it all works out, and this is the kind of things that if you don't get it, everything seems circular and weird about Newtonian mechanics. But let me first, before I go through the details of how this works, go back to this slide over here, all right? Now, what is equilibrium? Equilibrium is that these things cross. Now, let's forget about the crossing for a moment and just say that equilibrium is when for some reason the demand is here at this point and is not changing, okay? What's happening there? Well, what's happening is that the flow of the commodity, the quantity demanded, is constant, okay? Do we know which constant? No, we don't, all right? But we know it's constant. So the idea behind this type of equilibrium, this is called partial or Marshallian equilibrium. This is associated with a guy called Marshall. Although it's badly formulated, is exactly the same, right? Don't worry about the units here, he says. It could be any flow, so any velocity, but my feeling of equilibrium is that at least that velocity stays constant. So the amount demanded, the demand is a constant thing, all right? Then there are no forces acting on this, no forces of demand. If you read him, that's what he will say. Then he will say, well, what could be these different forces of demand? Then he looks at a shift, and then the demand goes up, you know? Then he will look at a movement along the demand curve and all kinds of stuff, all right? Huh? But nevertheless, and then what happens if you do this shift? Then again, it stays constant and you're in a new equilibrium. So this idea of equilibrium does intuitively coincide with Newton's idea of that the inertial reference frame, all right? So what for Newton is an inertial reference frame is that there are no forces acting on you. So you feel completely at rest, all right? So you're not changing your velocity. You guys can hear me again?
Yeah. I was wondering, you said no forces, but don't you mean equal forces? In opposite direction?
No net forces.
I mean no net forces.
No net force.
Yeah. But when I say no forces, I should say no force. Huh? The way they talk about it is like this, but you want to say no net force, or you could also say force free, right? It's a little bit circular, this business, right? So what does Newton say? He says, in an inertial, you're an inertial reference frame when there are no net forces, and when are there no net forces? When you're in an inertial reference frame, right? Huh? So there's a little thing that you worry about here. Now, the way Newton got out of it, he tried to identify at least one frame that he felt was inertial. And he started with the Earth. That's obviously not inertial because it's turning. Then the sun is not. And then he finally fixed something to the stars, and he says, that's it. Now, later writers realized that that's not inertial either, right? So the nebulae are also crashing into each other, and the space is expanding, and that's not inertial. So the way this was fixed was just purely theoretical. So what you do is you assume that there exists somewhere abstractly a frame that's an inertial reference frame in which particles at rest will go at this constant speed, and then there'll be no force. You can conclude there are no forces, okay? This is the current position. It's quite subtle, but in practice, you don't really worry about it too much, okay? So you say, as an engineer, mechanical engineer, you will take the Earth as just an inertial reference frame. And the Coriolis force, I mean, is so small, you don't really worry about it, you don't know very much. So the gravity force you'll worry about, that's not also not inertial, right? But the Coriolis force and all those other forces. So, you know, what would you do? You'll put in the gravity because that one is going to affect everything. Sometimes you don't. And there's all these other forces. I guess the Coriolis one is the only one you don't really worry about, unless you're building a satellite, right?
There's sniper rock.
They do? They worry about it? Meteorologists, yeah. So there is a TU Delft mechanical engineer with his sniper rifle sitting on the. Okay. Yeah. No, I understand. Huh? Yeah. Right.
I think the abbreviation IRF is maybe a bit This also stands for impulse response function.
Yeah. Anyway, so this is the point is we're going to take Newton's solution or the modern solution and apply that to economics. So in economics there's a huge discussion about partial equilibrium. And there's not, yeah, there was, and that it couldn't apply because there's all these other things going on. And then guys started doing something that's called general equilibrium, where they started modeling the forces from all other possible goods. It's called Walrasian equilibrium or general equilibrium. People like De Broglie and others who are very active in it. It's still a field of economics. Economists feel that it's gone nowhere. It's way too complicated, but they prove theorems that do all of this, right? And it's a huge thing, right? And there is some kind of helplessness, like when will we ever have all the effects, okay? Now, look at it from Newton's perspective. He says, look, if you just look at the motion of this pen through space, how are you going to get all the effects due to friction? You're never going to. What you're going to do is posit that there is at least one frame in which the whole thing just looks easy, okay? Where demand is indeed partial equilibrium. I don't want to make the cross, but just this line is just a straight line, and that's it, all right? So that's the trick, all right? So you say to yourself, look, I don't really care whether you're able to measure this in reality. I'm just imagining that there is, all right? And that thing, that mass, that is what I call the I element or my demand, all right? And then when it doesn't do what I imagine that it is, I'm not going to say, whoa, throw up my ear, my theory's wrong. No, I'm reminded of the joke of Mercury. I'm buttering the wrong side. I got to introduce other forces, all right? So I need a friction force, or I need some force of storage, or I need this, or I need that. Now, forces in economics are wants, so somebody wants this, and maybe somebody wants that too, and I forgot about that, right? Or look, you're going to say, I don't care about it, right? I'm just going to leave this thing will be approximate. It's not important, okay? So, as an engineer, this is the first place where you turn the whole thing around, right? You don't start a discussion whether Marshallian or partial equilibrium is true. You just take a dimension, it's inertial in this dimension. All right, now boom, I element. Then it's not inertial in this dimension, we're going to gravity, it's also an I element, and then, okay, then I'll have to figure out where that gravitational force comes from, if it is like a gravitational force, and blah, 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 all right? This is the trick. This is also the trick that Einstein played, right? So Newton still had a problem, is that there were two notions of mass. There is the notion of mass as inertia, that if I go against, not along, orthogonal to gravity, that the body will resist the motion, okay? That is what we're using here, all right, in economic engineering. But there is another notion of mass where you put it on a scale, and then you can just measure it due to gravity. Why are they the same? Why is the weight equal to the mass, right? Nobody could figure that out. It would seem to be a miracle. Of course, Einstein goes, he turns everything around. This is the trick. He says, I'm just going to assume it's equal and then figure out what would be happening to create this force. And then he sees that what it does is curves space, time, and then he has general relativity, right? And he calls that the principle of equivalence. So this is, in order not to get stuck in your reasoning and start making weird demand lines and think the elasticity as an economy, this is what you got to do when you're an engineer. You flip it around, right? You start with your laws, and if it doesn't conform, then you just go, all right, now let's go search for this, right? And in fact, that's what you do. So that's what electrical engineers do too. So the parallel of the mass, the analog of a mass, is an inductor. Now, you can make an inductor that's not linear, right? That has a changing self-inductor, right? But you give that to the electrical engineer, he starts building a circuit, he starts measuring, hey, this thing is not linear. So he calls you up, he says, hey, you give me a linear inductor. I don't want this thing, okay? I can't model with it, all right? And this is what you got to do. So this is Newton's first law. It will just make sure when you put down an I element, it really is an I element, okay? When you model demand, it's precisely how Newton says you should, okay? P is m times v. Huh? So what does that mean in multiple dimensions? Well, for Newton, it means that both the speed at which you're moving and the direction is a constant, okay? For economics, it means that the rate at which you're acquiring the goods and the proportion in which you are should also be a constant, okay? Now, what are these different internal reference frames that you get when you do a shift? So let's say here's a shift. Well, for Newton, this is just another internal reference frame. I just move this one to there, all right? Same stuff, just looking at it from a different perspective, all right? That's what a shift has to be. Even if it isn't, this is what it has to be. This is how you have to interpret it, all right? Then you can have junk like this, right? What is that? That's not a shift. So it's got to be something else. So there should be other forces acting on it. So there should be a shift here. This is some derivative, maybe dp, maybe over time that this happens. Then there's some force. What forces do we have? Well, we'll have the forces, the forces from storage, from friction, and you can make the list as long as you want. Gravity, all kinds of stuff. All right? So that's the program for after the break, is to start seeing how all these other effects, other than these shifts, how they affect this equilibrium point where you are, and why it might be that when economists measure this, they really aren't. They are measuring that, you know? And just to leave you on that thought, suppose you go back to this idea of Aristotle that, you know, that you take a body, you drop it, and at a certain point it comes at a cruising altitude, right? For us, it's friction, but for him, how did he reason, right? He reasoned that you didn't have friction, so how would you explain this? The only way to explain it is that the mass is decreasing, right? So somehow, or increasing, it's getting heavier. So somehow, if there's forces acting on the velocity, that only because the properties are changing that it's slowing down, you know now? So if the mass is increasing or decreasing, then you get these weird effects. But really, this is not what's happening, okay? The mass is staying constant, but you have a predictable way in which friction is causing the motion to change, right? So you can take a cart and it's just moving not with gravity, but it's going at a constant speed, and you just take a bag of stuff and you throw it on the cart. So what is going to happen? The cart will slow down. So it will go at a different speed than you expected it to go, if you simultaneously apply a force. But is it really, what is happening here, right? You just threw some mass on it, so you have two bodies now, okay? When you put them together, then things are changing again, all right? So every time you see an effect like this, you should look for the explanation within this idea of, the inertial reference frame being the starting point, okay? Let's take a short break, and then I want to go back to the real meat of the matter, the second law. We're done with the first law, and there are three. So we got one down, and we'll go now to the second law. This is the biggie, and although they're all big, but this is the one this is the famous FSM times A, right? Let me get a different color. Now, one of the things about this FSM times A, as everybody knows, the way everybody knows is that Newton never said such a thing. All right? I think he was way too clever for that. This is what he actually said. And he called a change in momentum, he called the force, all right? And the difference is significant. And this is what I'd like to talk about. Okay. Now, I told you before, the force, Newton called this the motive force. So he imagined something quite anthropomorphic. So he imagined this particle somehow having a motivation to move. In fact, Kepler had that too. He imagined angels pushing this planet to keep it going around in that circles and maintain this tangential velocity. So they kind of thought about this already in a sort of economic way, that it is a motivation to do something, the motive force. And then Maxwell later talked about a voltage. His term for it was the electromotive force. So it was the motivation of the electrons to move in a certain way, all right? So here, the notion of force and motive force is very close to the economic interpretation of a want, okay? So you can call it a desire to do something. It's just a little stronger version of a want. Or you may call it a necessity. That's even stronger. That's what I would call a constraint force, you know, so it will just generate any type of force. There's all kinds of terminology with it. Now, Newton's idea was here to say, all right, in his first law, he tells you when something is force-free, all right, when there's no net force acting on it, as Gilbert clarified so well. But he didn't tell you what happens if there is a net force on it. It's a little bit, it's completely analogous to, you start here in mechanical engineering, your first course is statics. You only draw free body diagrams, and you figure out that at any point in your trellis or whatever it is, there can be no net forces, all right? This is what you work with. Then you'll learn how there can be no net moments, But if there is a net force, nobody tells you what's going to happen then. The whole thing is flying apart, or nobody really knows what's happening, okay, in statics. Newton, at this point, tells you what is happening when there is a net force. And Newton's solution is to say that what that net force does, it changes the momentum of the body, all right? Newton actually says it was proportional to it, and then he kind of assumed the constant of proportionality would be 1, and then he calibrates the force this way, all right? So another way to think of it is that this is sort of the definition of a force, right? So what Newton does, he says, okay, I'm in this inertial reference frame, I have no forces, and now something is happening and a force is acting on me, right? What happened here? Well, obviously, I myself am not in an inertial frame anymore. With respect to something else, something must be happening, all right? And I must be able to observe that, and what I observe is my change of my speed with respect to the other one. And that change of the speed is exactly the acceleration if you look at it per unit of time, all right? And that's what this is saying. Now let's look at the economics. If you read Marshall, the book is full. He was in the tradition of the 19th century where this idea of a motive force was very, very pervasive in all scientific thinking. It's gone out of economics a little bit now. But then it was, he talks about the force of this. He makes direct comparisons to doors and other things, and or archways, I guess, not a door, an archway, and how this all relates. But all his comparisons are to statics. He doesn't have that extra step that if there's no balance, if the archway is not balancing the forces, that one of these blocks is going to move and fall out or boom, or something is going to happen, all right? And therefore, the step to calibrating what a force is and defining it is never made, right? So If you have two springs and they're in equilibrium, you can say, well, okay, the forces are equal. Then you can do some other stuff. You can say, all right, I put gravity. Then you can say the force of gravity is equal. But how big is this force? You don't know. And what is twice the amount of that force? You won't know. Right? The only way you know that is if you can calibrate it in some way against something dynamic. And this is what Newton does, right? He says, this is how you measure, you know, how big your force is. This is the definition of the force, okay? And you can say, well, how do I measure the change of momentum? Then Newton will say, well, just take your definition of momentum, right? In this case, that, plug it in there, and there you are. And then you can measure this, the guy, and this is exactly what Galileo measured, and then they could measure out what the force was. All right, he had another subtle argument that this mass could be determined by the weight. This issue wasn't resolved until Einstein did that in general relativity, but this is the way it works, okay? Now, this is what you got to do in economics as well. So thanks to the first law, you know what economic equilibrium is. You know that you can always put yourself in some kind of perspective, you know, to look at it, that the thing where you are in equilibrium, you can just look at that thing, okay? And if it's moving with respect to that perspective of yours in that inertial reference frame, you will know that there are some forces acting on it. So what you will see is if the quantity demanded is this V, that this V will have to change, okay? So here's a picture that I just typed movement along the demand curve, and I think this was the first picture, economics help. This is how they look at it. So here's the demand line. This is some quantity demand that they have. They call it Q. We'll call it V because of velocity or volume. And they talk about, economists, a movement along the demand curve. They'll have a contraction of demand, so there's less demand, and extension of demand when there is more. All right? So this V goes to some V plus dV, right? And if you look at the rate that happens over time, then that rate will be, all right? So when you move out of equilibrium, and you don't do this with the shifting and all this other stuff they imagine, we've already explained that away. It's got to be what they call a movement on the demand curve. All right? That movement manifests itself as the change of the quantity demanded. That change, and that's called the extension or the contraction of demand. All right? Now this is the demand extension. I already wrote it down here. That change has to be due from some economic force. So somebody's got to, economic force is a want, somebody's got to want this thing a little bit more. And that want makes that he's going to demand more of it and extend his demand. Or he's going to want it a little bit less, right? In which case, demand will contract, all right? Now we know that the slope of the demand curve is a constant. That's the inertia, or the inverse of the price elasticity of demand. All right? That won't change. So if we measure this, we can also measure how this price is changing. If we know how the price is changing, then we know exactly what the want is that caused this. All right? So here we have calibrated the idea of an economic force, or a want, or a desire, or a need, or whatever you want to call it, right? In terms of something that is observable, how the quantity demanded changes. All right? This gives us the dynamics, because now we know not only what the equilibrium price is, but we'll know how the equilibrium price is changing as a function of time. So we can think of the equilibrium price as a function of time, and then we can look at the change of this thing. And that will be, well, we usually call it P dot. It's also a function of time, and this is just the inertial force. That is the want the extra want that you get. Now, why would you want something more all of a sudden out of nowhere? Well, there must be something that's going on. Either your storage, your inventory levels are really low, and you think, oh my God, I have no apples, and I may get hungry tomorrow, so let me go, I want some apples, and you start buying the apples to replenish your inventory. Or it's high, you say, look, I'm getting sick and tired of these apples, I'm gonna buy less apples in order to, because I'm paying all this money for this inventory, and other guys want to give me good money for these things, so I don't need it, so you sell it, all right? Or you buy less, depending. Or it could be because you have all kinds of expenses that you got to make. These apples may be going bad, and they'll be rotting there. You got to buy some more. It can come from anywhere. Okay, that will be more of a frictional element. All right.
Okay, so beginning of this presentation, you said that we never use double process, never have this situation of demand and supply and several. And I feel this because we look at difference. And you start with a force, which is difference net force, integrated a net change of momentum,
right?
A net change of price, therefore a net change of velocity. In that way of thinking, we're not looking at a P curve or one-dimensional curve, but actually you're looking at a delta, like a P1 minus P2. You're looking at demand minus supply, or supply minus demand as one curve instead of the two curves in one graph with respect to some initial frame.
Right.
Yeah, you look at the excess demand function.
Yes, exactly.
So listen.
A delta, like a big delta.
Yeah.
That's the principle of relativity, all right? And I wanted to do that after the laws. So thank you for the question, but let's put it on the back burner here, because it's precisely what I want to answer there. Initially, I had thought in this lecture to first answer it, but what happens is that the whole thing is quite extensive, and then you forgot it when I'm doing it. So what I do now is also what Newton did, by the way. He formulated as a corollary to his laws, interestingly enough, right? Because, and you can see this, I mean, I like your question very much. That's why I'm going to answer it without answering it. If you look at this thing, right, this expression, right, you look at the second derivative, right, how in a second derivative of a velocity, right, the first derivative of the velocity, right, suppose I subtract some constant from this thing, and I take this derivative, right, I'm going to get the same thing. All right? So in this law is built in this idea that you're only looking at differences. All right? The way the law is framed, the difference has to be with respect to an inertial frame. What you're talking about is you have two masses, and then you would look at that difference, but then you give up the inertial, and then you're sitting on one mass that's also moving. So you have a bunch of complicated forces, all right? So then it's better to say, something else that I'm going to explain when I explain the principle of relativity.
Yeah, but I get it.
Yeah? But I just want to say here why Newton viewed it as a corollary. So if this is true, then this is also true, right? When this is a constant, and therefore,
I feel like economists always are trying to find what this constant is, and we don't care because we're also always at differences.
That's right. The irony of this is, I mean, why is this historical treatment so nice? Because you see the same mistakes get made. Newton made the same mistake. He felt he needed to come up with one inertial frame where he can set this equal to 0, right? And he couldn't find it. But then, it works so well that in modern formulation, we say, look, don't start looking for that. Just assume that, it's there in your head, right? And then in practice, take the Earth, It's just like in economics. Just in practice, take the Federal Reserve or take all consumers and call that 0, right? But that means you'll have negative numbers when you're consuming less than the nominal amount or something like that. But don't let that worry you, right? Okay? So the same mistakes get made, but were made by Newton that they are making now. So it's true, they're always worrying about this, but the impact of the first law is really to tell you don't worry about it. It's all going to end up the same. So another way to phrase the first law is that inertial reference frame is a frame wherein all motion looks simple. You can find other frames, it's just going to, the theory is just going to be a lot harder. Okay? So that's it. And that's a definition that's really nice in economics. Like an inertial frame, so Marshallian equilibrium is just a way of looking at it that everything looks simple, and then look at all the deviations from this standard of simplicity. Okay? These are the really deep ideas, you know, and I like that you brought this up, Gilbert, because it's one thing to listen to this, and then the other thing in your research to actually apply it and realize, oh my God, I am stuck with these economists looking for this magical zero that's never going to exist. And it's not going to make a difference on the results. I mean, huh? Okay?
Max,
yes.
could you repeat the explanation for how you get a shift among your liker? Because as I heard it just now, you said, oh, well, somebody I've got too much or little stored, so I want to buy more or less. It sounds as if the quantity comes to price, that is how we say price determines the quantity.
So I feel that your question is maybe confused because you talk about a shift, right?
Yeah,
but we mean a movement here, okay?
Yeah.
Huh? Yes?
I meant movement.
Yeah, but this is an important error.
He's mixing up stock and flow. So an inventory is a stock quantity, and a demand or a supply is a flow quantity. That's something different.
Yeah, but let's first stop here. There was a mistake here that I want to grab because it's so important, right? The movement of the long curve is something very different from a shift. A shift is just a choice of a different inertial frame, okay? All right? Okay, it's very important to keep that in your head because it's really essentially different. A movement, that's precisely when there is a relation between the quantity demanded and the price change, okay? Right? So the way they do it is they say, I'm moving along this demand curve, and if I move along the demand curve, you can just read off that if this is the change in the quantity demanded, this must be the change in the price. Huh? Okay?
Mm-hmm.
All right?
But that should be the other way around, right?
No, because...
So this is change in quantity demanded.
Yeah, but this is a negative number because you can run this axis backward, right?
Yeah,
huh?
Okay, but I mean the calls when price change calls change in quantity.
Yes. You are right. You're right.
But I think this has to do with the fact that economists, and they also do the macroeconomics with the ISLM curves. They make one curve where they actually meant to make two. So they put price versus quantity. What they actually mean, this is a combination of an I and a C. Whereas we're looking at the elements apart from each other. Look at one I element, make these graphs, the element graphs. And they somehow seem to be putting them together into one graph.
I would look at it slightly different, although you're on the right track. But first, your concern is that this graph you're reading like this, that this is the independent variable here, right? And this is the dependent variable, all right? That's actually not what economists do. This for them is the independent variable, and this is the dependent variable. They read it like this. Okay, that's number one. Then number two is every equilibrium they have, they'll draw one of these and one of these, okay?
Mm-hmm.
We don't do that, right? No mechanical engineer was ever determined equilibrium when you have some kind of crossing, right? Why not? Because first of all, this is two masses, two I elements. This one, the axis just runs the other way, right? So you get two masses, 1 and 2, and they are moving, right? Maybe this one is moving here, so this one is supplying, this one is demanding, and somehow they got to go in equilibrium. Now, what is this equilibrium? Well, they're going to crash into each other. It's just the center of mass motion, huh? However you do it. You know, you can crash them together, or you can look at it from afar and say the thing is just going in center of mass motion, and that would be on this thing, all right? Huh? Okay, but the way we view equilibrium is not always arising from collisions of two masses. Sure, momentum can be exchanged when you bang billiard balls together, but that's not that's only one way of changing the momentum. You can also take your cue and give it a push, right? Or you go blow at it. You can do all kinds of ways of changing it, all right? Huh? Okay. And Newton, he only tells you how the momentum will change if you have a net force. But he doesn't tell you where that net force comes from yet. He does that later, and then he describes gravitation and all kinds of different forces. But it doesn't need to be a C element. It could be an R element. It could be something completely different from a transformer or from gravity or something unrelated, all right? Huh? You have to see this as slightly more general than just bond graphs where you grab a C element and it's just any old force. Somebody's waving a magnet around and I don't know, huh? Okay, huh? All kinds of weird forces, all right? So here he only tells you that if the price is changing, there must be a force, but he's not telling you where that force is coming from, all right? So the economists, they try to solve it all at once. So they say equilibrium is here, and the other force must be coming from another demand, and one must be coming from supply. But I'm saying, no, it doesn't necessarily have to come from supply. Maybe you have so as Gilbert proposes, a C element. That means I have a storage, and that's my supplies. But there's no demand-supply graph associated with it. I just have supplies, maybe with an S, and I'm taking out of it, and that's reducing my desire for these apples since I got all that stuff in storage. You see? Huh? Okay? So you gotta stop thinking of economic equilibrium as only a crossing of two lines, all right? It's just like the picture here, also made by economists. You just have a demand curve and you just look at these motions. Now they just describe motions as sort of a phenomenological thing, but we're gonna model this. We're gonna say this is a want, and maybe if it's a potential force, then this is equal to what? Minus k times q. That's if it's a C element, but it could also be B times V if it's an R element, or it could be an external force. It could be anything at all. Okay? All right? So don't worry. Yeah?
I already got all of that. I wanted you to repeat your economic anecdote. Because as I heard it, the motivation of moving along the demand line or the supply line or access line came from the quantity and not from the price change. So I asked, could you repeat it so I can hear it again to get the intuition right in my head?
So it came from the inventory, not the quantity.
In my example.
Yeah,
so the inventory.
That's a key difference. Yeah. Because the inventory, that's what's causing the external force. That's your spring or your C element. And that will then change your price, and then by the demand law, the quantity. That's
right. But the motivation always comes from the force, the want, okay? Newton called it the motive force, okay? So a spring force, he wouldn't call a motive force. It's just a force. But once that spring is applied to a mass, it becomes a motive force that makes that mass change its acceleration. All right? Okay? In general, a voltage is not an EMF, electromotive force. No, it's just a voltage drop over a capacitor, right? It's nothing to do with motive force. But once that thing is applied to an inductor, it becomes the EMF of Maxwell, okay? It motivates this inductor to change the current that is going through it, okay? Right? That's how you have to see it. So this force is going to come from other elements. This is what we'll talk about after this lecture, how all these elements, blah, 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 right? Huh? Okay? But if you have your net force, then it will act to change this price, and that will act to change the quantity demanded, okay? Huh? So the motivation comes from the motive force. The motive force is precisely this force. Huh? In fact, a want, what we use, that has the idea and a desire, has this idea of a motivation in there, right? So you can say, I'm extending my demand, or I'm contracting my demand. And you can ask why. They say, well, because that's the motivation, right? Huh? So you observe this, but this is the motivation. All right? But then the other element that creates that motive force itself doesn't think of it as a motive force. It's just like a consequence. If it's a C element, it's a consequence for how much it has in storage, you know? And it's just inconvenient to have it, right? Huh?
And would we then, if we were talking about the spring, talk about a motive displacement?
Let's do that when we get to the spring. Let's focus here just on the I element, Joris, okay? Huh? Yeah. All right? Yeah. Huh? So we want to get this right. Huh? I mean, my answer would be no, because what I'm trying to do here is how Newton called it, and then make you see that it's the same as what this is. And Hooke dealt with these springs, so we can go to this. But you know, but I want to be sure that you understand the program. I want you to see Newton's precise thinking and how that precisely, in all details and all intents, translates to an economic thing. All right? Huh? And this is what is at the same time so hard and so easy about Newtonian mechanics. I mean, when you get it, you go like, yeah, well, of course, I mean, this is the causality, and how could I ever have gotten this wrong? And yet, after years and years and years, you still get befuddled, you know? So, okay? So, in summary, Newton tells you that you know what a force, or you know that something exerts a force if you look at the price movement, and that precisely is the motivation you give to the body to start changing its velocity, its state of motion, okay? This is also what he called the state of motion. Huh? The state of motion. He didn't use the word, huh? Or actually he used the quantity, huh? Huh? Of motion. Quantitatis. Yeah,
there's a nice Latin expression.
A Latin expression. Yeah. About quantis and motivation. Those two words are in there. Huh? Huh? And he says that this thing is. Huh? Okay. What do we say? We can compete, we can call it the price, but another way to see this is the willingness to buy. Huh? If you're demanding, otherwise it's to sell. Huh? Okay. The willingness to buy you get by adding up all your little wants over time, right? So you want this, I want this, and all of it adds up to a willingness to buy, all right? So the integral of your wants over time, as they accumulate, gives your total willingness to buy something, all right? Sometimes the band is described as your willingness and your ability to buy it, and the ability is the energy or the kinetic energy, and the willingness is the price difference, the momentum difference, okay? But these are all very fuzzy concepts in economics, as Gilbert can tell you. I mean, they search around for all this stuff, and very vague ideas, right? What you got to see is how Newton's laws make this very precise, and they do a little bit more than that. They just tell you exactly what it must be, what it would be, what then the ability is. It's really quite stunning, okay? For me, what it also explained to me what momentum was, right? I mean, I never had a good concept with it, but now when I think of it as the price, I'm just cool, you know? And that we'll talk about kinetic energy a little bit later, and you'll see that it's just kind of, all these things become clear, right?
Yeah, you see that at least in macroeconomics, they are really confused because they do not have a clear definition of storage and net change. And you really see that it's being confirmed, but that they have these different theories for growth and for non-growth, where growth they assume partial or non-partial differential equations, and they do talk about storage, capital accumulation, or labor accumulation, but they don't seem to know how to combine these.
No, because they don't have the notion of a force. They haven't quantified it, right? I mean, this Newtonian thing doesn't think about storage and position either. In fact, for Newton, all positions are the same, right? Huh? And then you can change the velocity. So where you are makes no difference. Makes no difference. All right. Huh? But then when we introduce a spring, we're going to give space, you know, just like Einstein did, give space a structure. So there is some point of zero that you can, because that's where the spring is relaxed. So all of a sudden you got a natural zero. You got a few more. There's another spring there or this. You know, so your space gets structure, just like gravitation will give it structure. Your space. All right. Huh? But then how do you translate that stuff that's going on in space with the stuff that's going on in the tangent space? Okay, that they don't know. And why don't they know? Because they don't know this. This is how one talks to the other, right? So if Gilbert talks about they have storage, but they don't know how to deal with it, well, that's because they don't know whatever comes out of the storage. I mean, there are guys in the futures markets, they talk about contango and backwardation and inventory levels, but this can't make it into normal economics because they don't have Newton's law. They don't know how to couple the two. So they only look at flow variables. There's no stock variables in macro. There's no stock variables. It's all about flows, constant flows.
Yeah.
So as if you only have I elements and you just put them all together, right? Huh? No friction, no other things. Huh?
The only place where I've seen it is in like the solo growth model.
Right.
You see this capital. That's where they start using the notion of some form of accumulation or storage, but they don't really know how to do it.
No, and even then,
inventory cycles too.
Yeah, Keynes did it with inventory cycles. But capital accumulation, yeah, maybe that's it. But the other thing you always got to be worried about is, I mean, are they really looking at machine hours per hour and it's really a flow anyway, right? Huh? In the solo growth model? Seriously? You know? Huh?
Yeah, but it's so weird because they do talk about it and they do mention that storage exists and it influences business cycles and it's very dominant how everything behaves in the economy, but they just don't integrate it within their knowledge or theories about how an economy functions.
Because they can't, because they don't have this. I mean, Newton, you know, you can have Newtonian mechanics, you just have this mass and it's moving with this velocity, yeah, you're cool, right? And here is your ground, I don't know. Huh? But now, or here is your ground. But now you say, hey, I want to be able to store, you know, this position. And now I'm storing a position because I know this is zero here. This is my zero position. The spring stores a position, right? And then you can say, well, I'll just couple this to this mass, right? Then how do they interact? Well, before people wouldn't know, right? And a civil engineer wouldn't know either. He won't see how his bridge moves. He just says it will go to a different position, right? Or if you do strength of materials, right? But Newton will tell you, okay, here's a force, here's the reaction force, and I know this force, I know how it relates to this distance here, and this force, I know how it relates to the change of this velocity. I'm done, right? And this brings me to brings me, I'm already right in the third law here. So here in the third law, Newton says something that sounds really kind of weird and trivial, but is actually quite deep, all right? Suppose, as usually say that action equal reaction, right? And I like to view that for every party, there's got to be a counterparty, right? So for everybody who's raising a price, somebody else is going the other way, right? He has to pay more. All right? Now, what's really going on here? One way to think of this third law is to make the thing happen what Gilbert is talking about. So you have this net force, and it comes from your spring or comes from anything, and it's going to influence the mass, all right? So you want to say something like this. You want to just add up all these ones and then say that has to go in there, all right? But now suppose this happens, but if I had done the integration in a different way, I would have gotten a different result, or a little bit later, I would have a different result, That cannot happen, all right? Because then I'm not saying anything here. It will depend on the path you took with this integral. It may depend on what time you started, how you did it, where you ended, how you extended the spring. This is no good, right? So what we need is that momentum is a conserved quantity. Now, when we say a conserved quantity, there's like this primitive idea is that it doesn't change. That's not what we mean by a conserved quantity. What we mean by a conserved quantity is that we can keep track how it changes, okay? That the stuff in minus the stuff out is the stuff accumulated, all right? So you have these ideas of conservation that all of a sudden the level of the water in your bathtub went up, and then the bathtub of your neighbor went down, but there is no link between the two. That cannot happen, right? The only way the level in your bathtub can go up is when you open the faucet, you put water in, or when you open the sink, the water goes out. And the sum of those two, if you add it over time, that's precisely how much water you have in your bathtub, okay? So there are two ideas. One is that you can keep track of what's going in and what's going out, and that the difference over time can be added up in a way. Nothing disappears or comes out of nowhere, all right? Okay? So, if you say action equals reaction, what this is really saying is that if you have some kind of point here, a massive point, and you pull at it this way, then if the thing is not moving, there must be something pulling on it the other way, right? Okay? So if you have a member like this, and you look at a point and it's not moving, and you're pulling here, then something must be pulling from the other side. Otherwise, something weird is happening, okay? But the way you should understand this is a slightly more general, and it's sometimes called the D'Alembert's principle. And this is, I made a little drawing of this. So the way you should understand this principle is that a mass is a sort of container for momentum in the same way that a bathtub is a container for water, all right? And then what the forces do is they are the flow of the momentum. That's what F is P dot says, right? Okay. And then when you push it on a mass, what you're doing is you're pouring momentum in it. And the amount of momentum, and I gave this as some sort of a liquid with the red thing, is just increasing, right? So you have some heavy cart and you start pushing. It doesn't start moving immediately. It has to pick up momentum. So as you keep pushing, you're pouring this momentum in, but there's all this friction. So the earth and the ground is pouring momentum out, but you push harder than the friction force is, and then it will acquire a net momentum over time, okay? And you can keep track of all these flows, okay? This is what Newton's third law says. The other way to think of it is that you can think of momentum as a state variable. So if you draw a plot, you can say this is the momentum and this is the position. Why? Because the velocity you add up to get the position, but space doesn't disappear on you. There's not a hole all of a sudden, you know, and then you have less space, right? And the same thing with momentum. It doesn't disappear on you. The only thing you want to know is where am I, right? What's the net result of this? Okay? And another way of saying this is that price becomes a way to measure value. Okay? So value, there's many notions of value, but this is one notion of value. When you add up all the wants, okay, and you assign that as a value. So the units will be so many euros or dollars per item that you have here. And then what the I element does is it creates this value. A value becomes a state variable. Okay? You see, if you didn't have the third law, what you could have, you have all these forces, and sure enough, momentum is changing, but all of a sudden, yeah, it flips down again for whatever reason, right? It doesn't really have memory of what happened, and it may depend on how you pushed on it, okay? If you took a car, you pushed first a little lower, then harder, and then that can happen, right? Now, here I plotted the kind of free body diagram that we would do. So free body diagram, what will it do? You will have all these forces, and they are the flows of momentum, and then you see how much you have. And if there's no net force, that will mean that the amount of momentum in this body won't increase, so this thing would be zero then, if F net is zero. If it's not, then the body would get more momentum, all right? Now, the way any kind of node works in economics is in the same way. So you have all these people, I want this, he wants that, all this stuff may balance, okay? Nothing will happen. The prices will stay constant. But now somebody wants something a little bit more, okay? Something changed. He's going to want that more. There's going to be a net want here. And that's going to jack up the price. That's the only place it can go. If you open up the faucet a little bit and you're taking out the same amount, the only place the water can go is in the bathtub. All right? This is what the third law says. All right, so now look at this picture. This was also just on the internet. And here is from a popular science thing where they show, this was also the first hit I got when I don't know what I typed in, something related to this. You can kind of see that what this person is doing is really thinking of supply and demand as a bunch of forces acting together. Now, they even have a balance. He thinks of this as a weight, okay? And then demand, it is a counterweight. And then if that force, I mean, I would probably call it more a torque, but no matter, right? The idea is there. And then if this force is higher than that, so he got this wrong. I mean, this guy is pushing and this guy is pulling, so I don't think they're in equilibrium. This is shooting off. But, you know, he probably wants to be pulling on the other side, right? But that's a small detail. But you can see that this idea that if there is an imbalance in those forces on this balance, and here's a literal balance, either the price has to fall or it has to rise, okay? So there's a subtle difference here between the second law and the third law, a subtle addition. The second law just says that any change should be change of momentum should be a force. And this one says it's the net thing, and you can integrate it out and then just get the price or the momentum. All right? Now, with those three laws, we're basically there. Now, next lecture, what I'll do is I'll clear up all this business about how you do this in practice now with all this stuff, and how you can see this as a it's called the principle of relativity. It's also a thing of Galileo's that Einstein ran with. All of mechanics is a story of Galileo, Newton, and Einstein. Those are the three figures, I think. They did it all. Huh? We'll talk about his principle, and then resolve all this business of the minor signs. That would mean that we achieved our goal of getting this thing straightened out to a single graph that we can deal with. And then I'll move on to energy and take this graph and show how you can use it to define what you mean by energy and why it corresponds to something that you would call profit or surplus. We'll talk about the co-energy, and the fun will go on. Until then, I'm going to bid you a nice continuation of your sunny day. And Thursday we have Gilbert that is talking. You will go first, and if there's any time left, I may continue the discussion from last week on the writing of the thesis. And then, so Max Broekman and other people, Joris, if you want, you can upload your thing. As long as you're not going to be disappointed when we don't get to it, because the priority is Gilbert, I'll just start filling time for Thursdays to go through further thesis writing. Okay?
I have some small questions, Max.
Yes.
First is the Zoom link for the